After stoichiometry is used just to compare things, you get the idea of ratios and getting over this psychological hurdle of ratios in chemistry as opposed to ratios in scaling or recipe settings. We need to talk about what happens if you have different amounts, different starting amounts of things. In the previous calculations, we had some idealized scenario. Given some amount of one thing, how much of the other thing do we need, and how much product will form? Now we need to look at it as, if I have this amount of one thing and this amount of another thing, how much product can I make, and how much is going to be left over? And this is where the real stoichiometry starts. Once we worry about limiting reactants, sometimes see the terminology reagents, right? Reagents, just a way to describe chemicals in general. Reactants talking about the things you start with in a chemical reactants. And it's not as easy an idea as you would expect. It's not the one you have less of. It's the one that you stoichiometrically have less of, all right? So it's the reactant present. The reactant present in stoichiometrically lesser amount. All right, and I'll abbreviate limiting reactant as LR from here out to save some time. These words look scary, right? Stoichiometrically lesser amount. Well, you have to include the ratio. That's the key. It's not necessarily the one you have less of. It's the one you have proportionally less of. All right? So with that, we have the idea of an excess reactant. And obviously, you could have reagent there as well. Obviously, I'll abbreviate that ER for excess reactant. And that's the reactant present in stoichiometrically greater amount. And it's just like this process where, present in lesser amount, greater amount. Reactant present in, once again, stoichiometrically greater amount. If any of those words seem confusing or intimidating, ignore them for now, because the process is really straightforward. Okay? It's a psychological hurdle when the terminology isn't what we're used to. It's a ratio, it's a proportion. So what we're going to do is we're going to go back to the bike example because it's super dumb and anybody can do the math and anybody can visualize it, so that when we take that same principle and apply it to real chemical equations, we have a process in place. Step one, look at a problem and panic, but step two is we have a process in place, let's follow that. So if you forgot our top secret bicycle formula, 2 wheels and 1 frame give you 1 bike. All right. In previous problems, we set it up as, given this, how much of this do you need and how much of this can you make? But is that a realistic scenario? Like, let's say you actually have this bicycle factory and you walk out to the warehouse one day, and so we'll say given some amount, and we'll just say like 300 wheels, right? And 200 frames. What would we ask? Like, what is the number of bikes that could be built? All right, and then we can ask a secondary question, and that secondary question is the amount excess, the amount of parts left over. And these two terms are vocabulary terms of interest. The number of bikes possible is going to be our theoretical yield, and then the amount of parts left over is going to be our amount excess. Right? So, like, if you were using our previous example of Kool-Aid, where you take 1 packet, 1 cup of sugar, 2 quarts of water, let's say you had an ocean full of water and a warehouse full of sugar and 1 packet of Kool-Aid. Well, you're going to make 1 batch of Kool-Aid, and you're going to have an ocean minus 2 quarts of water, and you're going to have a warehouse minus 1 cup of sugar. So the amounts you have starting out do matter, and sometimes you're going to have extra. In this case, let's take a look at how it works. And this setup builds on the previous setup, and it's critical. So this is a little different than I see people do things traditionally. It seems simplistic, but it pays off in the big picture. I think too often we're so focused on teaching stoichiometry that we ignore how stoichiometry gets applied. So this is going to be a real building process in terms of formatting things for much bigger problems later, and we're going to do them all the same, all right? The setup is always going to be the same, and that's critical. So we're going to list out, like last time we said, start out with what you have, right? And put it in the first box, use a ratio from our balanced chemical equation. Now, though, we need to take a look at what we need, all right? So let's see how this breaks down when we set it up. I have 300 wheels. All right, same as we did before. First thing, what's given in the first box, and then use a ratio from the balanced chemical equation. There's 2 wheels for every 1 bike. Sorry, for every 1 frame. All right, which gives us, in this case, 150 frames needed. So I have 200 wheels. Sorry, 300 wheels, as I wrote. You need 150 frames to use up all those wheels, and now let's compare that to what we actually have. I have 200 frames. And balanced chemical equation says that for every 1 frame, we've got 2 wheels needed, right? And so we end up needing 400 wheels. So looking here, you need 150 frames to use up all the frames you have. You need 400 wheels to use up all the wheels you have. And a quick comparison here, I have 300 wheels, I need 400 wheels. I don't have enough. And we have to compare diagonally like this, and I think that's something people traditionally miss, because this is talking about the wheels we have. This is the number of wheels we needed based on the number of frames that we have. So we can identify at this point our limiting reactant and our excess reactant. I have 300, I need 400. I don't have enough. I don't have enough wheels to use up all my frames, so my wheels must limit how much product we can have. So that's our limiting reactant, using the terminology that we had before. Label it on the have side, because that's what you actually have, right? For our frames, we have 200. To use up all 200 of my frames, or sorry, we have 200, but I only need 150 frames to use up all the wheels. So in the back of your mind, you can say, we're going to have some extra frames, right? So I have 200, but I only need 150, right? And so you can look here and say, have 200, need 150, there's 50 extra, 50 left over. The reason this is so important is our limiting reactant is what determines how much product can be made, all right? So I'll make some room, I guess, here, right there. We have now compared our reactants to each other to find the limiting reactant. Now we're going to get an amount excess and find out, based on our limiting reactant, how much product can be made, how many bikes we can make. So let's get that amount excess very quickly. It's just subtraction. To get an amount excess, it's just what you have minus what you need for the excess. And in this case, I have 200 frames, and I need 150 frames. And that means that I have 50 excess frames. All right? And that is one of our parts to deal with. All right. Oops, that was part B. All right? So I think that this is critical. Setting things up in this way allows anybody to walk up and see what happened. This is what I have. This is what I need. This is what I have extra of. The difference between them is how much extra I have. Anybody can look at this and see it. And the traditional way of teaching this is to just take your amount of one reactant, work it all the way through to products. Take your amount of your other reactant, work it all the way through to products, and then compare. And it becomes kind of a hassle to do things like the amount excess. And it becomes a huge hassle to do solution stoichiometry and gas stoichiometry. And that's really, really, really important. We need something that's going to apply to all our stoichiometry calculations, not just getting stoichiometry done right now. So let's look at our theoretical yield. Our theoretical yield is going to be based on the limiting reactant. And we'll write that down in a bit. But this determines how much product can be made. It's the one we don't have enough of. So I'm going to take that 300 wheels, and I know that for every 2 wheels, I can make one bike, right? So in this case, our wheels are canceling out, and we end up with 150 bikes possible. And that was our answer to part A. Our theoretical yield, based on the parts we have, we can make 150 bikes, and we have 50 frames left over, all right? And then you could wave that around and say, 50 frames, I need another 100 wheels, and I can make another 50 bikes, or whatever. And you could calculate a percent yield if you were given an actual yield. So there were two primary steps there. Compare your reactants to each other to find the limiting and excess, and then compare the limiting reactant to your products to find out a theoretical yield. I think it wouldn't hurt to write that down. So our basic first steps, you're going to compare the reactants to each other. And the reason you're going to compare the reactants to each other is to find the limiting reactant and the excess reactant. So you need to then identify the limiting reactant and the excess reactant, right? And what can we do with those? Well, the limiting reactant determines how much product we can have. So you're going to use, in fact, I'm going to call this step 3. You're going to use the limiting reactant to find a theoretical yield, right? And to do so, you're going to compare the limiting reactant to your products. So we've got two comparison steps. Those comparisons are based on ratios from the balanced chemical equation. Compare the reactants to each other. Compare the limiting reactant to the products, all right? This is to find a theoretical yield. This is to find which one determines how much product we can make and how much is left over. So we can sneak in and call it step 2, right? I know I said 2 steps earlier, but you can get some amount excess, all right? And it's all laid out very cleanly. Anybody can look at it and see what's going on, and it's a little bit different than stoichiometry is traditionally taught. So we'll look at another situation, but let's right off the bat change our system from bicycles to an actual chemical reaction. All right, so we had last time 2 hydrogen and oxygen gas giving us 2 water. As we look at it, synthesis reaction, 2 to 1 to 2 ratio, that's what our stoichiometry is based on. And as a side note, that could be, well, I declare it's a mole ratio, which is the same as an atom ratio, which is the same as a molecular formula unit ratio, which is the same as a concentration ratio, or volumes or pressures for gases with a few variables held constant. So we'll just say given, in this particular case, 30 moles of oxygen, and we'll say 20 moles of hydrogen. What do we do? Well, we had 2 basic steps. Step 1, well, 2.5 or 3. Step 1, compare the reactants to each other. Take what you have. It's the same idea as what we said before. What you have, right? And we're going to use that to find out what we need, so we can figure out which one is our limiting reactant, which one we don't have enough of, and which one's our excess reactant, the one we have more than we need, right? So in this particular case, we're given that 30 and that 20 moles. So I have 30 moles of O2. That's given, goes in the first box. I've got 20 moles of H2. That is given, it goes in a totally different first box, but that's what I have. I'm listing what I have. Now I'm going to compare from our balanced chemical equation, there's a 1 right there, 1 mole of oxygen for every 2 moles of H2. We're just scaling it, right? And it's the same as bikes or anything else, 2 wheels for every 1 frame, so I'm going to need twice as many. It's the same idea, but just follow the process, ignore the math, it's just dimensional analysis. 30 times 2 gives us 60 moles of hydrogen, right? And then 20 moles of hydrogen for every 2 moles of hydrogen. And again, this number is coming from right here. Everything after the first box comes from the balanced chemical equation. There's 1 mole of oxygen, right? So 20 over 2, right? 20 wheels, 2 wheels for every 1 frame, so we're going to need 10 frames. It's the same idea, right? So we end up here with 10 moles of O2 that we need, right? And how do I know it's what I have and it's what I need? Because I wrote those words out. If I get distracted, which I inevitably will, I can look at this and pick up exactly where I left off, all right? So the things we might ask for, right, we'll just say like some amount excess, right? And we said that's going to be based on our limiting and excess. I have 30 moles of oxygen. I need 10 moles of oxygen. Do I have enough, right? If I go to the store with $30 and something costs $10, not only do I have enough, I have more than I need, and they're going to do subtraction to tell me how much money I get back. So this right here, have 30, need 10, that's more than I need. That's got to be my excess reactant. And to sneak in a term there, that's stoichiometrically more than I need by a ratio. And I want to look at that in a moment here. So as we look at the hydrogen, have 20. I have 20 moles of hydrogen. I need 60 moles of hydrogen. You go to the store with $20, something costs $60, you can't buy it, right? You don't have enough. So in this particular case, the one you don't have enough of, at least stoichiometrically, is your limiting reactant. So we can get our amount excess over here by taking what we have of our excess, right? Like it's all laid out very cleanly. What I have of my excess minus what I need of my excess, right? Have minus need. In this case, that's 30 moles of oxygen minus our 10 moles of oxygen, right? Which means that I have 20 moles of oxygen excess, all right? And we'll call that our part A or whatever. We know how much we have left over. Now we need to know how much we can make. Our first step was comparing the reactants to each other to find the limiting and excess. Our second step is to compare the limiting reactant to our products to get a theoretical yield. And that's what we had written down before. I'm going to erase this. We're done comparing our reactants to each other, and now we need to use just the limiting reactant to find out about our products. So our limiting reactant was the hydrogen, and I'm going to start with what is given, right? 20 moles of hydrogen. That's what I have of the limiting reactant. Have of the limiting reactant. I wouldn't label that, but I think it's semi-useful for right now. Start with what you're given. Everything after that comes from the balanced chemical equation. 2 moles of hydrogen. I already compared the hydrogen and the oxygen in the previous step. Now I'm comparing the hydrogen to my water, right? So my limiting reactant to my product, and that's going to tell me about my theoretical yield. 2 moles of H2O. And so we end up with 20 moles of H2O as our theoretical yield, right? So that's part B or whatever. And we could work in a percent yield or whatever. All we'd have to have is some given actual yield, all right? 20 moles of H2O is our theoretical yield. That's possible, right? Given those starting amounts, right? It's theoretical. All right. I want to do one more to finish this video out, and we'll do something that doesn't have as simple a ratio, just so we can see something different happen, all right? So there's a common reaction that maybe we can do as a demo sometime, and that's the Thermite reaction, where you mix aluminum powder with rust, and you get aluminum oxide and iron. And they use that as a very exothermic reaction. They use it out in the field to weld railroad tracks together. And there's some interesting videos on YouTube you can look up for that. But the reaction is a single replacement reaction where you have aluminum metal and you mix it with iron oxide, and we'll just say iron 2 oxide in this case. It doesn't really matter. I only have one chemistry joke, and it's iron oxide is an ugly compound. In this particular case, then, it happens. You would check your activity series. Aluminum, the thing that's by itself, is above iron, the thing that's in the compound. So aluminum is more reactive. It will replace iron. So we end up with aluminum and oxygen bonded together now. Aluminum is a 3+, oxygen's a 2-, crisscross and reduce. There's a 2 there, and there's a 3 there, right? It's a solid. You're making solid aluminum oxide. And then our other product has to be whatever's left over, which in this case is the iron, right? So you're taking rust and turning it into elemental iron, which is pretty cool, all right? This is not balanced as written, so let's go through the steps of that. I know it's really frustrating to set up a table of reactants and products. Part of science is describing the process in such a way that anybody can see what you did and proving what was done in a logical way. We've got aluminum, we've got iron, and we've got oxygen. 1, 1, 1. Product side, though, we have 2 aluminums, 3 oxygens, and 1 iron still. All right. I tend to either work my way top to bottom or just throw some numbers at the board. It doesn't really matter. Aluminum is by itself, iron is by itself. So we can start by just saying, all right, I'll fix the oxygens maybe. Reactant side, put a 3 there. And that's going to fix the oxygens and screw up the irons, right? And I guess we will have to. So we've got 3 oxygens and 3 irons and 2 aluminums that we need. We can solve the aluminums by putting a 2 there, and they match. We can solve the irons by putting a 3 there, and they match. And anybody can look at this and say, when it was blue, it wasn't balanced. Now that it's red, 2 and 2, 3 and 3, 3 and 3, it is balanced. That's key. This is a mandatory step, in my opinion, because this is what tells you that's balanced, right? People who know chemistry and who know math and are comfortable with this stuff can look at that and squint at it for a while and do the algebra. Anybody can look at this and say the numbers match. This is really, really important. So we'll give some starting amounts here. We'll just say given 20 moles of iron oxide, iron 2 oxide, and maybe like 10 moles of aluminum. All right. We want to do the same thing. We want to get a theoretical yield, and that theoretical yield in this case will apply to both products. And we want to get some amount excess. Our 2 steps. Step 1, compare the reactants to each other to find the limiting and excess reactant. Step 2 is going to be to compare the limiting reactant only to our products to get a theoretical yield. And somewhere in there we can find our amount excess. All right? Same process as before. What we have versus what we need. And that's going to give us our comparison. In this case, I have 20 moles of iron 2 oxide. And I know from the balanced chemical equation there's 3 moles of iron 2 oxide for every 2 moles of aluminum, right? So 20 times 2, 40, divided by 3 is like 13 1/3. So we'll just write it down that way. 13.3 moles of aluminum. Moles of iron oxide cancel out. As we look at the other reactant, 10 moles of aluminum, and we know that for every 2 moles of aluminum, right, from our balanced chemical equation. From our balanced chemical equation, same number. From our balanced chemical equation, same number, 3 moles of iron oxide. Okay, so we have 30 over 2, that gives us 15 moles of iron oxide that we need, okay? And we're comparing, given 20 moles of iron oxide, right, I would need 13 moles of aluminum. I have 10 moles of aluminum. I don't have enough, all right? So I have 10 moles of aluminum right here. I need 13 moles of aluminum. Label it on this side as limiting reactant and excess reactant, because this is what you have. That's your pipe dream of what you might need. 10, 13, not enough. 20, 15, more than enough. So this has to be our excess reactant. And again, we can do a very quick calculation to get our amount excess. And it's labeled like any distraction. Oh, but look, I have 20 of my excess. I need 15 of that same thing. So it's our have minus our need, right? And in this case, we have 20 moles of iron oxide. And we're going to subtract that 15 moles of iron oxide. And that'll get us 5 moles of iron oxide excess. All right, whatever part we want to call that, we'll call it part B. Part A would be to identify your limiting reactant and excess reactant. From here, what matters most? Well, excess reactant doesn't determine how much product we can make. It's only the limiting reactant. So that's what we're going to use. As I look here, I'll make some room just for this step. I don't need to know about my excess reactant anymore. We are going to compare our limiting reactant to our products to get a theoretical yield. And you can do that in 2 steps or in 1 step. I'll show it in 2 steps, and then maybe down here I'll sketch out what it would look like if you were writing a lot less, which is what I would recommend. All right, take what you have, 10 moles of aluminum. Everything after the first box comes from the balanced chemical equation. For every 2 moles of aluminum, there are 1 mole of Al2O3, our iron oxide, right? It's a 2 to 1 ratio. So we end up with 5 moles of aluminum oxide as our theoretical yield. Given 10 moles of aluminum, I can make 5 moles of aluminum oxide, right? Similarly, start with what's given, 10 moles of aluminum, and for every 2 moles of aluminum, and I want to point out that this much of this work is exactly the same, and that can give us a shortcut in terms of writing later. In the top now, I want to know about my iron, 3 moles of iron. Again, first box, what's given? After that, from the balanced chemical equation. 1 here, 3 here, 2 here, right? So we have 10 times 3 is 30 divided by 2. We do get 15 moles of iron possible here. 15 moles of iron, right? And this is our theoretical yield. Our first step was to compare the reactants to each other to identify the limiting and excess. We had a little secondary step there, finding our amount excess. And then we compared just the limiting reactant to our product to get a theoretical yield. And I do want to sneak in here how I'm going to set up problems in the future, not just because I'm lazy, but because I'm lazy. And that's start with what's given, and I'll try and color code this in a logical way. We had 10 moles of aluminum, all right? So this problem's done. But let's look at how I could have saved some writing. Since this part right here, this and this were the same, I'm just going to write that once, and then I'm going to put those in as 2 separate calculations. For every 2 moles of aluminum, right, I have 1 mole of aluminum oxide, right? So I'm going to do 10 times 1 divided by 2. And that's going to give me my 5 moles of aluminum oxide. And I'm just going to throw in this other calculation, just totally separately. I'll say, 3 moles of iron, all right? So what we're looking at here is the blue with the red, that's what happened there. The blue with the green, that's what happened right there. But I can show it in 1 step, and that saves, half the writing in this particular case. So we said 10 times 3 over 2, that's 15 moles of iron. And this is our theoretical yield, but it's the same with less writing. So where we need to go from here, we're going to have to do something other than moles. Maybe we'll practice some more percent yields, and we'll keep building on this until we get to the full spectrum, the big picture of these problems. But again, the key, showing your work in a logical way so anyone can walk up and look at it and identify what you have and what you need. And so this is going to be a really good comprehensive setup by the time we're done.